All right, hello everyone. Welcome to this talk on how to test rendering code and how we do it at Frostbite. My name is Jon Valdés, and I've been for the last 8 years at the Frostbite Rendering team, where I've worked on frame graph, global illumination, post-processing, strand hair, and a bunch of internal tooling, among other things. Lately, I've also become an engineering manager because I can't sit still, so yeah, keep changing things. But this isn't a talk where we have the answers to things. We don't claim to know what the right way to test is. And this is a talk where we would like to push other people to also present what they have so that we can learn from them. If you think our system is not as good as yours, please present it. We would love to see it. This is mostly a talk on things we have learned and things we believe are important. But I'm sure there will be disagreements, so it's going to be interesting. All right, so some required reading. There's been a few people that have been talking about testing rendering code for a number of years. One of them has been Aras Praskavicius. He used to be at Unity, and he wrote a bunch of blog posts on how they tested their rendering engine years ago. These two are really good. Our system, when I joined Frostbite, seemed to be heavily inspired by these blog posts. Can't claim that they were, but you could see a lot of similarities. So yeah, this one's definitely a foundational piece for us, I would say. Then we have Bart Wronski, who wrote this great blog post on how not to test graphics algorithms, in his opinion. I do agree with most of his points, but in the end, we end up doing all the things he says you should not do. But we also have a bunch of things that allow us to do that without as much pain as he says he had experienced in previous places. So that's something that I would like to focus on, the ways that we make screenshot testing not as painful as other places. Finally, Keith Stockdale from REAC gave this great talk at GDC this year that I highly recommend you watch. He explained how they test their shader code at REAC, and they found slightly different ways to solve very similar problems to the ones that we were trying to solve with our infrastructure. So it was very interesting for us to watch, and yeah, really great talk. All right, so what is Frostbite and why do we care about testing so much? So Frostbite is Electronic Arts' internal game engine. This means that every game team within EA can use Frostbite if they so wish, and the engine is not available to anyone outside of the company. We don't sell it, we don't have it on GitHub, it's just something for internal usage. And Frostbite as a team within the company provides the technology to the rest of the company, to all of the game teams, and Frostbite helps those game teams both develop new technology that they need, and also we just help ship the games. So whenever our technology isn't working to the level that the game teams need, we jump in and we help. Because Frostbite's mission, Frostbite's purpose, like the reason we exist, is to ship those games. So I said we don't sell the engine. The engine just exists so that these games can ship. So we very much have the game team's priorities in mind for everything we do. And these are the games that we make. And it's not a single type of game, right? We have all of the sports games, which we can generally bundle in one group: FC, Madden, UFC, NHL, even PGA. They tend to have similar demands on the engine. They tend to be stadium with a crowd and some players in the middle doing things. Then we have open world games like Skate, which is multiplayer open world, and Need for Speed, which is mostly single player open world. Then we have Dead Space and Battlefield, which are first person shooters, and well, you have also single player and multiplayer. And we even have RPG games with things like Dragon Age. So all of those things have extremely different requirements for, or like goals for what they want the game to be. You might find that Dead Space is not very concerned with whether or not grass is beautiful. And similarly, FC is probably not very concerned whether the open world streaming system works really well, because they don't have a use for that. But that means that the engine needs to be very flexible and be able to cater to those types of games, to all the types of games that we make. Now, this means that stability and making sure all of those systems work well is one of our priorities, because every time one of our game teams gets a new version of the engine, they find things that don't work as they should. They say, hey, this feature used to work on the previous game that we did, and now it doesn't. That's an issue. Or they say this was faster last year, or they just enabled a feature that had never been enabled before with certain settings, or some other features also enabled, and everything breaks. Or they just find that new feature that we built just doesn't work as they need. So all of that is really important for us. Now, to have all of this working, we have been building a testing infrastructure for the last 10 years or so. And the structure is pretty simple in brush strokes. We have all of our data and code and the reference that we compare our tests against, in the case of screenshot tests, all of that lives in Perforce. This is one of the points that Bart Vronsky was talking about, is that you get desyncs between different Perforce workspaces if you have the code in one place and the data in another. We don't. Code and data go together, always. If you do an integration from one branch to another, the code and the data go together, and that way you can make sure that the tests work as they should. You can have confidence that that works. Otherwise, if you have things living in different places, you're going to have desynchronization problems, and it's just going to be painful. So yeah, first thing is everything lives together in the same repository in Perforce, in the same workspace. Now we have all the data in Perforce. We have a caching mechanism that I won't go into, but the engine grabs that data, and we have a test runner which invokes the engine, and it instructs the engine to run the tests. Then the engine grabs the data from Perforce, runs the test, and communicates back to the test runner what the test result was. In the case of screenshot tests, the test runner grabs the reference screenshot from Perforce and compares the reference screenshot with whatever the engine just produced, and then it sends all of that information to the central database that we have, which is a networked database where every single test that we run ends up in. So all of the tests run by the CI, but also all of the local tests that you run on your personal machine, all of that ends up in the central database, and that makes it very easy to share results between people. Then we have a few tools that communicate with the test result database. First, at the bottom, we have the test dashboard, which I'll show later, which just collects all the information from the CI of which tests are passing, which ones are failing. We have a test result inspection tool, which allows you to go into the details of how a test is failing or reasons why. And then we have a dedicated screenshot tool, which we have built to make the inspection of screenshots easier and faster, mainly. And these two last tools communicate back to Perforce to update the reference screenshots. So whenever a test changes and the results it produces are different, and an engineer goes in and looks at the images and says, yep, this is expected, this is exactly what I wanted to see in the test, then they can update the image in Perforce, and that becomes the new reference image. Now, our testing dashboard, this is how it looked in 2016. This was very quaint, very nice. We had 3 branches here, 2015 render, dev render, and dev. And we tested Xbox One, PS4, DX11 forward, and DX11 deferred. And that was it. That was all that we had in our dashboard. That was pretty nice. Now, look at this image and now compare it to 2024. This is what we have now. The number of platforms is massive. Now we have PC DX12, PC Vulkan, Series X, Xbox One, Xbox One X, PS4, PS4 Pro, PS5, Switch, iOS, and Android. At least we got rid of DX11 and Stadia. And we have thousands of test suits, and each of these green or red boxes in the dashboard is not one test. That is a test suite. So there's boxes in there that have hundreds or even thousands of tests. So the actual amount of tests that we run is just massive. We run pre-submission tests. We run a small set of these tests as pre-submission to make sure that we don't completely break the engine for everyone. And then the bulk of it is run as post-submission tests. So if something is red, we don't block people from submitting. And we just block people from submitting something that would break the CI. That would break the pre-submission, yeah. Anyway, so what test types do we have? Well, if we go to the traditional testing pyramid, it looks kind of like this, and you can see the typical thing with the unit test at the bottom, and then as you go up, things become fuzzier and slower and less reliable. For us, there's a few that I won't really go into. Unit tests, if you can use unit tests, do. We use Google Test, works fine, no regrets, nothing incredible about them. They're just industry standard at this point, and they just work. If you can use unit tests, do. That's it. We also have integration tests, which is the load level and do things kind of test. This is the same thing that Rare has. You can watch their talk. It's just a level with some node scripting that changes the level in some way and then checks that things have ended up in the way that you expected. And then we also have editor tests, which, you know, our editor is very big, and we have a bunch of tests that click on things in the UI and check that the UI state is what you would expect. So yeah, those ones I'm not going to go into anymore. I'm going to focus on the other ones that we have. So performance tests, these are very important. They're pretty new. We've only had them for a couple of years now. But what they do is that they keep running flybys of specific levels that we have, and they record a few minutes of gameplay and then take statistics of which things they have found, and they take CPU and GPU markers, and whenever something deviates from the history, we get an alert. And it can deviate up or down. If we've had alerts coming that say, well, this piece of GPU code suddenly became 50% faster. Is that expected, or did you just disable something inadvertently? This works pretty well. We do have significant manual triage work with these. We have our QA go and triage every one of these alerts. So it's not free, but it is useful. Now we also have what I would say is shader unit tests, like proper unit tests. We invoke specific functions in HLSL code, and we pass particular parameters to the function, and we expect the output of that function to be something concrete, and we just assert that just like you would in Google Test or something, like in a unit test. This is a system that is built outside of the engine. It's C#, and a nice thing is that we can enable warp for this, so you can actually run it without a GPU, which is nice for the farm VMs. If you have some VMs that don't have a GPU, they can still run these tests. We are not using this system a lot yet. Only the physics team is using them right now, I think. They're pretty neat, and we would like to expand on them because they allow you to do very fine-grained testing. The Rare guys, they have a pretty similar system to this. They don't test individual functions like that, but the system is kind of the same. So go check them out, go check their talk for more info on this style of testing. Then we have what I would call unit tests. These ones are C++, and they are in the engine. And I can't, in good conscience, call them unit tests because they do involve communicating with the GPU, executing things on the GPU, and then reading the output back. So they are not as unitary as you would like in theory. But the idea is that you execute C++ code that then communicates with the GPU, and you check that the whole thing works as expected. And then you can do asserts, just like you would in unit tests, or you can have a predefined result that you are expecting, like buffer data or even an image, and you can check that the output is the exact image that you expected. this doesn't have any thresholds of allowing slightly different results. This is a memory compare operation that it does for checking the validity of the result. In this case, we have this test which instantiates a frame graph, so our frame structure. It executes a light call radix sort, and it passes this unsorted data that we have defined here, and then it checks for each of the, well, it executes the frame, let's say, and then it grabs the output of that pass, and then for each of the elements in the output, it checks that the sorting is correct, that every element is less than the element that comes after that. So this behaves pretty much like a unit test, and it's extremely robust, but it also has a problem, and it's that you have no infrastructure. You don't have a texture streaming system, you don't have a terrain system, you don't have any of the big systems that we have in the engine. None of those are instantiated for this. None of that exists. So anything you want to do, it is pretty much like a unit test. You have to mock things, or you have to, if you need to instantiate a big system, you have to do it yourself, which means it can be a lot of work to get those things up and running for one of these tests. Then we have screenshot tests. These tests are the bulk of our testing, and this is pretty much the load a level and do things kind of test. In this case, we have, you can see in the image below, we have a bunch of different setups, and each of those setups has a different camera. And then we have several node script scripts. And each of those, what the system does is that it goes from camera to camera, and for each camera it executes certain commands to set up the test. Like in this case, this is a distant shadow cache, or cascaded shadow maps test. And so for each camera it sets a different setting for the cascaded shadow maps, and then it takes a screenshot, runs some more commands, and goes to the next test. And then it keeps repeating until it runs out of tests in that scene, and then it exits. So once we have the screenshots, we need to compare them with the reference, and for that we have an industry standard, which is NVIDIA Flip, and we don't use it. Instead of that, we use a very bad per pixel metric. This metric has been there since forever, and nobody really knows why that's the metric we use. And there's a lot of people that have been annoyed by the metric, but at the end of the day, it's not as bad. Like, it just works. It's not great, but it's not terrible also. And so we haven't had the need to change it. So yeah, that's how the metric is calculated. And yeah, that comment is in the source code. But yeah, we get away with this really bad metric because we have extremely stringent thresholds. So this is a comparison of a failing and a passing test. And you can see the line moving back and forth, and it's very hard to see the difference with the naked eye. But the pixels that become red when the mouse goes up, those are the pixels that are failing. So that test, the threshold is so small that even zooming in this much, you can't tell the difference between the failing and the passing pixel. But we still consider that a failing pixel because the threshold is slow and we care. And the second thing is that the test that we do is per pixel. So if any single pixel in the image fails the test, then the whole image is considered failed. And, you know, people tend to go crazy. It's like, well, like a single pixel is slightly above a threshold and you fail the whole thing? Yes, we do. Because a single pixel can be really bad. In some situations, it's terrible. Like this is a case we had where there was a single pixel in an image like this. It was really bad, and an auto test caught it. And, you know, that's the bad pixel, is the center of the sun. The center of the sun was black. And that was terrible. And an auto test caught that problem. We had a division by 0 at the center of the sun, and it just exploded. So yeah, we care, and we get away with things because our thresholds are super small, single pixel. But then there's hardware differences. Each IHV that you try things on, each OS version, everything that you change in your setup tends to change the screenshots slightly and then makes the screenshots fail. Our solution is to have per IHV and per platform screenshots. That means that the number of reference screenshots skyrockets. Like between the time that I started writing this talk till the time that I finished, we got about 1,000 images more in our reference screenshot folder. This, you know, I have a thing there that says pain threshold. It is painful, and our objective right now is to reduce that pain with better tooling, and that's what I'll go into later. There's other people that say, well, just make your test hardware independent. Just make sure that your test is going to execute the same on every single piece of hardware and you'll be good. And that's very hard. It's extremely hard because there are many things that are IHB or driver or compiler or OS dependent, like just a Windows update can make your tests different. The biggest difference is texture filtering, because that's not perfectly defined in the standard, particularly if you go into an isotropic filtering. That's just like every device on the planet does a different thing. But there's many more things that are different, and I have a fun one here, which is that transcendental functions like sine, cosine, tangent, all of those, they have a minimum precision according to the DirectX standard, but there's no maximum precision. So you can run into cases where different hardware decides to go deeper into that precision thing. So there's a shader toy here that I ended up writing a while ago that tests implementation of sine and compares it with a software implementation of sine. And you can see that different GPUs give you different results. And every single IHV that I have tested the shader toy on gives me a different image. So yeah, even if you avoid texture filtering and you're very careful what you do, if you have sines, if you have cosines, and you have anything like that, you can still run into these problems. And yeah, it's very, very hard to avoid. So we have these two systems that are trying to test the same kind of things, but they have different trade-offs. So for the render tests, our unit-like tests, we have exact comparisons. They're extremely robust. Once you get it working, they basically never break. They are hard to set up initially because you might have to set up a lot of code. If your system is not designed to be tested in this way, you might be in for a lot of pain to try to get things set up for this. But then long-term bliss. Once it works, it's done. Works, and it works forever. So really recommend it. On the other hand, we have the screenshot tests, which uses inexact comparisons, so everything is a bit fuzzy. That means that the robustness can vary. You can have tests that are very brittle, and we do have some of those. And you also can have tests that are quite robust, like our lighting tests, for example, are pretty robust. They tend never to break, so yeah. Setting them up initially tends to be very easy, particularly if you can copy-paste another test. You can just copy a block of a level or even copy the level itself, and yeah, you can have it running in like 1 or 2 hours. You can have a new test running, and it's pretty easy. The problem is that it has maintenance costs long term. So you can set things up quickly, but then you know that over time you're going to be accumulating maintenance on those tests. And this gets us to screenshot flame wars. Bart Vronsky is not the only person that doesn't like screenshots. Even within our team, we have people that don't agree with the testing strategy. And yeah, it's very hard to convince people on the other side of this war. So there's my theory is that we have two different kinds of thinking. We have people that think in a very mathematical way, where they say, hey, if I want to test that the blending works as it should, I just blend white and black at 50% and the output should be 50% gray, right? that's what it should be. And you can test that, and you can assert that, and you can make sure that that works exactly as it should. That's one viewpoint. The other viewpoint is there are questions that aren't easy to answer. Like, do we have banding on our gradients in the volumetrics, or is the TAA converging well? Like, you can see the aliasing is nice or not, or is this blue that we have in the sky the right shade of blue, or is it the wrong shade of blue? How do I calculate what the right shade of blue is? That can be very hard. Do we have visible noise patterns on GTAO? Or is the pattern that we have now better than the pattern that we had before, or is it worse? Those things are not mathematically quantifiable in many cases. So there are reasons for sometimes going with screenshots instead of something more like a unit test. First, it's like setting complex cases in code. Sometimes it's just not viable. If you want to test the interaction of multiple complex systems, you have cascaded shadow maps falling on strand hair, and the thing is motion blurred, and it just gets too complicated to test in a very isolated way. And then correct is, I say that's a moving target. First, you often can't mathematically define what correct is, because the system is too complex for us to say that. But also, a lot of rendering techniques are approximations, and as we change the approximations, correct changes. So you can't just, like in the case of a blending operation, yes, you can say that 50% is the right thing. But if you're doing something like accumulating GI over several frames, at the end of the day, there's a point where you can only rely on what looks good is good. And the higher you go, like the closer you get to the hardware, the easier it is to think in terms of, mathematically correct things. But the higher level you go, if you go into systems that are very complex and have many moving parts, it's very hard to get there. So people that work in higher level systems, like if you're trying to integrate strand hair with volumetrics, you can't be thinking in that very mathematical way, because it's very hard to assess what is correct or not. And finally, the ultimate reason is games have to ship. Ideally, you would just consider how much it's going to cost you long term to maintain these tests versus set them up, set the perfect tests up initially. But if the system has to be in the game by next month, you can only spend so much time building the perfect test. And it's better to have some tests, even if they are imperfect, than having no tests at all. So, yeah, pragmatism at the end of the day is something we have to live with. In any kind of engineering requires trade-offs, and that's something we all have to live with. Now, it's important to try to build high-quality screenshot tests. I would say we haven't found a way to make something in screenshot tests that is both high quality and easy to build. So you can have something that is very easy to build, but then it takes you a very high effort to maintain. Or you can have something that is hard to build initially, and then it might be lower cost long-term to maintain. There's also the corner there where you have high initial cost and high maintenance cost, but yet let's try not to do that. So a few ideas on what to try to do to have tests that are robust and also relatively easy to set up. Try not to reuse data between tests, because if you need to change a test and something else reuses the data, you're going to break other tests. So try to have the tests as isolated from each other as you can. Then having fully deterministic paths that you can enable for testing is extremely valuable. At Frostbite, we have a deterministic mode for our tests, which disables things like the random camera jitter and things like that. Even if you're not testing that randomness in the auto tests, that is a tiny part of the code, and you can still test everything else in a deterministic setup and make sure that it works at least there. And that is extremely valuable. If the non-determinism of certain things blocks you from testing everything, that's terrible. So we do have, even for example in strand here, we have some code that depends on atomics to accumulate things, and depending on the order that the different GPU cores accumulate into value, you can get different results. So we ended up building a deterministic accumulation that didn't rely on atomics, which is much slower, but it does allow us to test the whole thing and make sure it works. So this is important in my opinion. Then if you can, go for exact comparisons. If you can't go exact, go as low as you can for the thresholds. And the tighter the thresholds are, the less things can move around or vary before you notice. And if you can go exact, that can give you a lot of peace of mind that things are working as they should. Then typical thing for testing, decouple your tests. Don't test 5 systems at the same time. Test just like one thing or maybe 2. This can be hard. Like all of these things, the more you try to do them, the harder they are and the more costly they are to do. But if you have the time, if you have the opportunity to do it, I think it's really worth it. And then one very important thing in our opinion, which the REAC guys mentioned in their talk, is delays in testing. Just the idea of waiting for a few seconds and hope that everything has settled by then. We try to avoid that as much as we can. This node setup on the left is a system that we have which synchronizes the distant shadow cache, and it works. It's an event system instead of a delay system. So there's a node that says, okay, the shadow cache is finally ready. We are now ready to run the test. Until the cache is fully ready and stable, no screenshot can be taken. But also this means that you don't wait arbitrarily delaying your tests when the cache is ready or is already fine to take the screenshots with. So this allows us to first be a lot more robust because we never take a screenshot when we shouldn't, and also be faster because we don't have to speculatively wait and hope that we are done. So we don't have to wait more than we should. And this is an issue for our farm, for example. Sometimes our farm is running multiple tests at the same time on the same machine, and that means that those tests run slower. And when that happens, tests can start failing simply because the machine is running slower than usually. But if you don't have delays, if you have everything being event-based, then you can avoid that. That's crucial. And yes, we still have a screenshot delay thing there because sometimes we, trade-offs. Sometimes we haven't spent the effort to add an event system to something. And for those cases, we still rely on delays, but we try to do it as little as possible. And I mentioned speed. This is the speed at which our tests run. This is screenshot tests. The render unit tests thing run much faster. Those ones run at like 300 tests in like a minute. It's basically running at 30 FPS. And the screenshot tests run pretty fast, like one test every 1 second or 2. It depends on the test, and it also depends on the resolution, because whenever a test happens, it needs to send back the results to the central database, and that bandwidth is important for the execution of the test. So yeah, if you have tests that are a lower resolution, that makes the test faster. Now demo time. Okay, so I modified our source code so that most of our tests would fail, and I run our auto tests, and you can see this is the tool that we have to inspect our auto test results. It's called Overlord, and we use it to check the result of our tests. So in this case, for example, we have this image, which you can open it, and it lets you inspect the pending and the reference. We also have a heat map for which pixels are more or less wrong, and then the red pixels are the bad pixels that are making the image fail the auto test. So you can move left and right, you can zoom in and compare specific pixels. So yeah, this is very useful to inspect the results of our tests, and it gives you a lot of information about it. The problem we have with this is that for every image you want to inspect, you have to go back to the list and go to the next one, and it's a bit painful. It does allow you to update the image in Perforce. So this, if you click this button, it will communicate with Perforce and store the new reference image in Perforce CL. So that works well, but it's not really fast when you have a lot of auto tests failing. You can see here that there's 1,682 images being generated. So if you want to inspect all of that, you're going to be there for a long time. So for that, we have another tool we call Underling, and this tool is designed to be really fast to use. So you can select an image like the one before, you can go zoom in and pan and everything. It shows you up here the RGB colors for left and right for the pending and the reference, and it's very fast to check because we have all of the images loaded. You can see down here it loaded 1,300, so I guess we didn't have 1,600. Some of the tests don't have images, and it loads all of the images, and then you can just left and right, you can just use keyboard shortcuts to go image by image and inspect all of them quickly. You also have filters here, so you can just say like ocean, and you get the 3 tests related to ocean somehow. So it's a very fast tool that just loads all the data initially and then just works quickly. More things that it has this detail, which is a highlight failing pixels mode, which is extremely useful whenever you are hunting down for that one pixel that is failing and it's very hard to see. This tool is very useful. And we have this sort by PSNR, which puts the images that are failing by the highest difference, it puts them first. So as you go down the list, the last ones should be failing by very little. And yeah, indeed, you can see there's only one pixel that is failing here, and it's, which one is it? That one in the center. And you can see that it's failing by 3 in the R channel, 3 in the red channel, in the green channel, and 2 on the blue channel. So we use this tool all the time, and we also have a shortcut. We press A to accept the image, and that will add it to Perforce. You can see the icon there, and that means that the image has been added to Perforce. You can also do things like select like filter and go through all of the images. You go, okay, yeah, these ones, okay, that's just some texture filtering, whatever. Let's keep going down. Yeah, single pixels, this one's like a bit more, but yeah, that's fine. Single pixel here and there, yeah, those are fine. Cool. Same kind of error. Single pixels here and there. Oh, that's 4 pixels. Yeah, that's interesting. But yeah, I'm okay with that. Keep going down. Fine, 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 fine. Okay, accept all of them. Accept all visible. This will add 22 images to Perforce, and we're good. And all of those images have been added to Perforce, and you can submit them now. So yeah, this is a really useful tool, and the fact that it's fast and it's designed for power users, you can just quickly move back and forth, inspect images really quickly, and you don't have to wait for anything. This is the kind of tool that I believe can make a real difference for engineers working on these systems. So highly recommend spending time on building something like this. Right, so how do we get to this point? If you don't have a system like this, what can you do to get to a point like this? I would say that at Frostbite we work, like, the improvements are based on pain. whenever there's people that feel working with our testing system is too painful, something happens. We need pain for things to move. This means that we are never fully satisfied with our testing. There's always some pain because we always get to the point where someone flips the table, and that's when we get improvements. So yeah, and then the pain goes down. But we always have a certain amount of pain, and that means that nobody is fully happy with the testing ever. And I suspect that might be a universal thing. At Frostbite, at least, we have seen two ways to get to that point, to get improvements. One is to convince leadership, to go to leadership and say, okay, listen, our engineers can't work like this, our QA can't work like this, we need to spend effort on improving our infrastructure, we need to do this and this and this, and we need 4 people full-time for 3 months to build this new system that will make our workflows good. The other option is that someone flips the table and just goes in and does it. And honestly, both systems work. If you have a dedicated team building something, you're gonna get results. Like a well-oiled engineering machine produces results quick, but also a fed-up engineer that knows exactly what they want can get a lot of work done. In our case, screenshot tests, rendering unit tests, and shader unit tests were built as this kind of grassroots projects where someone was just fed up and decided to spend a week doing it. At Frostbite, we have something we call Action Week, which is a week where you can work on whichever projects you believe are most important. And people have used a lot of their action weeks on improving these workflows, and it's been really, really great. On our infrastructure, the same thing. Everything that is fully blue here is a project that started as someone's Action Week project, basically. And everything that is dashed is a second project that has been built to replace a previous grassroots project. So for example, the current dashboard that we have is a team has built that dashboard, but it's replacing a previous dashboard that was built by a single engineer because they were fed up with the state of things. And the same thing with the test result database. Now we have a fully staffed team that is building a new thing, but the previous one was just a couple of engineers that decided to go in and do it. Now we're not done. As I mentioned, we don't claim to have the final thing in our hands. We don't claim to have the answers. And we're far from done. But there's things we know we need to do. First of all, there's several teams within Frostbite that don't care about single pixels being bad. Like our UI team is like, why would I care that a single pixel is black? I just want to know that the window is in the right position and it has one button here and one button here. I don't care if a single pixel is bad. Right now we're experimenting with resolution scaling as a hack for this. So we basically render things at much higher resolution and then downscale to reduce the chance of a couple of pixels making the whole thing go bad. Seems promising, but we don't know yet if it's gonna scale. We also have no good workflow for comparing screenshots between different platforms or branches. If we want to say, hey, are the screenshots on Series X the same as PlayStation 5? That requires a lot of manual work, so that's not great. Or are the screenshots on the release that we just made the same as we have on the main branch? We need to improve our tooling for this. We also need a workflow to accept screenshots on other platforms. Like say you're looking at the screenshots for PlayStation 5 and you say, this screenshot is good and I'm happy if all other platforms have a screenshot similar to this. We don't have a way to do that. Right now you have to go through every platform and check the screenshots and go, yep, this is good, this is good, this is good, or this is bad. So that kind of thing is what's currently driving pain, and we can do something about it.
Hi, John from the future here. So I've been getting some feedback from the team on things that I
forgot to mention during the talk, so I'll try to cram some of those here. First, we have an extremely tightly controlled farm. So any change in GPU hardware, OS version, driver version, console SDKs, all of those things will affect the screenshots. And that means that whenever the farm needs to be updated for whatever reason, like the GPU that we were using is very old and we can't buy any of those anymore, and so we just need to buy new different GPUs. Whenever that happens, all of the screenshots are going to break, so we need to update them, but they're going to break on every single branch that the farm is testing, which means that if we have, say, 2, 3, 4 branches, then we need to update the screenshots on all of those branches, and that can get quite gnarly. So this is a very careful rollout that we do, and yeah, it takes effort to do. Now, another thing I want to mention is that the game teams used to not be able to run our integration tests and screenshot tests. And that was because of the way the data was set up. It was set up outside of the engine directory. And whenever the game teams got the engine, they just copied over the engine directory and to their branch and then run with that. And it was just not possible to grab also the test data. So now we've been moving all of that test data back into the engine directory so that all of those things can run. But that brings an extra complication in that the game teams do modify the engine in some cases. And as I mentioned, correct is a moving target. So for example, if a game team decides to change motion blur, because they've decided to go with a different trade-off of quality, then maybe they want it to be slower but higher quality, or they want it to be faster and lower quality, whatever it is. If they change that code, the auto tests for the motion blur are going to break. But that doesn't mean that that's bad. That's just a different trade-off that they decided to go with. And so what we're building now is a way for game teams to have their own reference images for those things that they have modified. And then we need a three-way comparison between what the engine was supposed to produce, what the game team has decided to produce instead, so they have their own reference image, and then we have the image that the game is actually producing. And those three things can be different images. So that adds an extra complication to our tooling, to our testing, and yeah, everything is complicated. Anyway, back to our regularly scheduled programming. So in conclusion, testing for us is always from slightly painful to very painful. We haven't found a way to make testing painless, but it's still extremely useful and extremely we get a lot of value out of it. So we highly recommend spending time on building testing infrastructure and testing systems that you can rely on, because they make your life a lot easier in the end. And you can make a difference, even if it's a single engineer that has a week to spend on testing. You can make a difference on the quality of the product. You can make a difference on the engineer workflows and QA workflows. And you can make a difference in the team velocity in the end. So yeah, testing is good. Who would have thought? And yeah, I'd like to thank everyone that has cared about our testing infrastructure over the last 8 years that I've been here. This is a big list, and I'm still missing a bunch of people because I couldn't access the repository for a couple of projects that, like our current dashboard. So I'm missing a bunch of people here. It goes a bit against what I said, that a single engineer can make a difference. But for example, the ones that are in blue here are single engineers that have made a difference in our testing infrastructure just because they felt they could do it, even if it wasn't their main task at the time. So yeah, you can just spend a week, go in, add some nice testing thing, and make your life better in the future and make the lives of everyone around you also better. Right, so that'll be me. Thank you very much. And now for some Q&A.
Thank you for that, John. Very, very exciting. And as you said, lovely, lovely discussion in Discord that's been engendered already with lots of wonderful memes. So we've only got about 10 minutes and we have a ton of questions. Alper, I'm going to skip over your question on frostbite branching. It's a fabulous, interesting topic, but it's, I think, out of scope for the time we have here. So I'm going to move on to Antoine Coid's question, which is echoed in a couple of different other places around IHVs as well, which is Warp's level of reliability. I mean, Claire posted a bunch of really helpful links about how they're updating it for ray tracing and things like that. But what problems have you seen in how well Warp is maintained? How often do you see divergent behaviors from IHV from what Warp does? And there's another question bundled here somewhere else, which is what do you do on platforms that you don't have Warp? What does your testing harness look like?
So first of all, we don't use Warp a lot. As I mentioned, it is a tool that we find pretty neat, but we haven't. First, as someone commented on the Discord chat, it's had limitations in that it doesn't support certain features, and apparently that's been improved now. But we've been limited in which ways we can use Warp, and that has made it more difficult for us to adopt it. But also, we haven't built many new features that that we could use this kind of testing in since we added the warp support. So it's not a type of testing that we use a lot yet. The physics team is currently the team that is using warp the most, interestingly, because they do have a bunch of code that runs on the GPU for their cloth solver and hair solvers. So they're the ones that have the most experience, not the rendering team, interestingly. For other platforms that we don't have Warp, well, that's our general status. We just run on the hardware. On every single platform, we run on the actual hardware. And on PC, we run on the machines that we have in the farm. So yeah, our testing structure, testing strategy is generally running the actual hardware. And the Warp thing is just a thing that we can do to make our lives better in some cases, but it's not our main focus. There was something else you asked, but I forgot.
I don't remember the exact question either.
All
I
right.
think let's move on. Thank you. Pivoting a little bit, Ryan Salamul Singh, I apologize, asks, have you considered using the screenshot comparison harness to find the best looking graphics for presets, like especially if you replace a distance metric with like a perceptual difference metric or something like that. Basically, if you try to subvert your debugging tool for other purposes yet.
I don't think we have. And so the thing is, at the engine level, it's not generally us that decide those presets, it's the game teams. And it's generally technical artists that start playing with all of the knobs that the engine has and start tweaking things up and down until they find something they like and they set those as presets. And as at the engine level, we provide all of the things that they can tweak, but we don't build the presets because the presets are also extremely dependent on the content itself. So if the game has content that exercises some specific part of the engine a lot, the presets might be very different. Like the presets for FC are going to be very different from the presets for Battlefield or the presets for Dragon Age. So from the engine side, it would be very hard for us to predetermine that.
Let's pivot again a little bit. There's a question from Adam Sawicki. Does your automated test system track regressions and point to the developer who submitted the bug? And do you ask them to fix, revert the change, or just create a new Jira ticket for someone to fix the bug?
So our farm system does track which CLs introduced breakages. However, our farm is not fast enough to run the entire set of tests for every single CL that goes in, which means that we don't have culprits, we have suspects. So we just say, well, between this CL and this CL, we have all of the things that were submitted, and something broke here. So the people that submitted in that range get pinged. You get a notification on your workstation that says, did you break this? And then you have to say, no, it wasn't me, or you have to claim that breakage and say, yeah, it was me, I'll fix it. And then for the social part of accepting things, yeah, it's you're supposed to fix the things that you broke. Whether or not you do that, well, people will start screaming at you if you don't fix the things that you broke.
Yeah, and a kind of related follow-up to that from Daniel Olson of Turtle Rock is he asks, in the example of the black pixel in the middle of the sun, how much of that, once you've made the diagnosis, how much of the follow-up on that is manual? Is it something you guys automate? Like, do you generate like GPU captures automatically using like a Pix, begin end capture API or some other command line tooling to generate that and then hand that off, or does everyone basically kind of start from first principles with local reproduction and local testing? And Balder Carlson, who's the author of Render Doc, who many of us know, asks kind of related question: what's sort of scripting, and do you do any sort of attempt at automated bisection if you do have that?
So Keith Stockdale from Rare, he did say that they did have automated render doc captures for breakages like this, and I think that's a wonderful idea. We don't have that. We right now we just try to reproduce locally. If we can't reproduce locally, we just remote into one of the farm machines, just take it out of the farm, remote into it, and try to repro there, and then take a render doc capture there. And for things like doing bisection of, like, you have many CLs where things broke and you have to find the exact one that introduced the breakage, we use the tried and true method of asking a QA person to just go and do the bisection. It's not great, but it works, and we don't have to do it that often, thankfully.
Yeah, I can't remember if you specifically addressed this, John, in the latest version, so I apologize. But Jamie Hayes asks, do you happen to have any numbers or even a hand-wavy guess with the image-based test failures, what percentage of time you just replace the ground truth, versus tracking the actual regression? And then, Balder asks a similar question actually online. Do you have guidelines or policies on what the justification is needed? What sort of policy process do you have to avoid, people just mass approving their deltas and things like that?
We haven't had the need for that. We work on a personal responsibility kind of system where you're expected, like, there are certain types of failures that we're all very used to where just a single pixel fails, and we kind of know that people are going to be fine with that. And whenever something more substantial than that shows up, people know that they'll have to ask the owners of that code to see if that difference is right and is correct. As for percentage of failures, we do update screenshots quite often, but they also catch many things that we have to fix. Like the screenshots catch, I would say, 1 or 2 issues a day, at least, of people submitting something and then forgetting that there's that other feature somewhere that they didn't think of. So yeah, we're not strong arming people into not accepting images or anything. It's more of a social contract, let's say.
Very Scandinavian.
You could say that.
Jeremy on this, we'll finish up with this one. Asks, can you share? And he says several, but I'm just going to ask for one more. Anecdotes where the test suite caught an important regression that would have been really hard to diagnose with more manual means. We had what I'm calling black hole sun, and I'm wondering if you have another great anecdote along those lines you can share for us to wrap up.
I'm thinking of that song. Hard to think because it happens basically every day. Like the screenshots break constantly. I mentioned that the dashboard was green, and that's the reason that I had a screenshot of a green dashboard is because that was the only time that it was green. And the screenshot for now that I also had for 2024 was quite green. And the reason it was quite green is because we were going through a release process where we had been nailing down bugs for 3 weeks when I took that screenshot, and that's why it was pretty green. But usually there's a lot of things that that are constantly breaking and getting fixed, and it's we just find it all the time. Things that are found by the farm that are hard to diagnose, like we've had driver bugs, like someone mentioned the driver producing inconsistent results every time you run something. And yeah, we've had that, and the farm has caught it, and that's been an issue because that test becomes something that you can't depend on until that driver is fixed. And we might have to disable our testing for that feature until that is fixed. That sucks. Yeah, I don't know.
No worries.
I can't think of any other funny anecdotes.
I'm sure we've got time to post them in Discord later if any of your team members want to show up as well and roast some tests. Thank you again, Jon. Excellent talk. Thank you for the Q&A. And then we'll continue our conversation in Discord. We'll be back with our final talk of the day, which will be Kevin Tedisco's Ray Tracing Diablo 4 at 10:45 Pacific in about 14 minutes. Thanks, everyone.
Thanks.